to Einstein, because Einstein didn't just live in a world of incredibly strange various things trying to travel fast at the speed of light, like you get in relativity, or things which are as small as an electron in quantum physics. He also looked at some problems which were a lot closer to human size and just human lives in general. And one thing that he looked at was a problem that someone had come up with in the 1820s, because he'd been looking at pollen grains and suspended in water, and he noticed inside it that there were some little particles he could see, but they weren't staying still. They were jiggling about all over the place in lots of different directions. And people later on looked at these in more detail and thought, oh, perhaps there's just a current moving through the entire thing. Perhaps there's a current moving through the water, and this is pushing all of these particles about. But then they found they could have two particles which were really close together, so they should have been inside the same current, and those particles would wobble in completely different directions. So what was going on? What Einstein did is he took this Brownian motion and he showed that what you could think of it as is something which is being bashed on lots of different sides by lots of even smaller molecules in water that you can't see, but that they must have some sort of distribution of their speeds and going in a random direction. And he proved the mass of it and showed that when you're just moving normally, if I were to walk across this stage at constant speed, the distance I've travelled in 1 second will be half of the distance I travel in 2 seconds. And if I travel for 4 seconds, I'll have gone twice as far again. So we say that it goes linearly with time. You double the time, you double the distance that I've gone. But with these particles moving about, what you can do is you can measure where they started and then see where they are at time t later and work out how far they've gone. And instead of it going as t doubles, the distance they've moved doubles, it's as t is times multiplied by 4, the distance they've moved doubles. If the time is multiplied by 9, the distance they've moved triples. So instead of going like t, the distance they travelled goes like the square root of t. And there are a few numbers in front of that as well. Then you need to actually work out exactly how far they go on average. And what Einstein did is basically he did the maths and worked this out. But I'm going to give a little demonstration just to give you a bit of an idea of why it might be going as root t rather than t. And I'm going to do something simpler. Because that Brownian motion, that's something which is constantly moving all over the place. Whereas what I'm going to do is what's called a random walk. And all that means is that basically if I stand here in the middle of the room, I've got 3 chairs on that side, 3 chairs on that side, and I'm going to randomly decide to take a step either to my left or to my right. But if I take, normally, if I think, oh, I'll probably try and go the same number of steps left as I go right, where's the most likely place for me to go? If I just do pick lots and lots of directions randomly, but I've got an equal chance of going that way, where's the most likely place for me to end up?
Right now.
Yeah, right back in the middle. But here's a different question. If I stop after a little bit of time, on average, on average, what is the distance away from this point that I will be? So I don't care, so this is one distance away, but so is this. So is the average going to be 0? No, what's it going to be? Is it going to be bigger or smaller? It's going to be bigger, because no matter which way I go, if I don't end up exactly back here, I'm always going to end up with some distance away. But it's very unlikely for me to just keep on going the same distance, the same direction lots and lots of times. If I did go the same direction lots and lots of times, that would be like just moving straight, like I had before. And then you say the distance that I got away would be given by my speed times by my time. But I'm ending up slightly further back. And basically, if you work through the maths and like cancel out all the things that are going to be equal, then you find that it ends up with this square root. And this is something that you'll see in lots of places. If you've got some sort of perfume or some sort of I don't know. One thing. If you put some washing up liquid into your bowl, the time that it'll take to spread out is related to this law. If you put something smelly in one corner of the room, the time that it'll take in order for you to be able to smell it elsewhere would be related to this law, apart from the fact that when you get to this sort of size, and you're in a room with lots of heating, it gets a lot messier. So it can't quite apply to everything, but it is a very important part of what we call statistical physics. Einstein worked it out by saying, there's lots and lots of these water molecules bumping around, and we can't know what each one of them is doing. But what we can do is we can look at all of them and we can work out an average of what they're doing. And this is something that we use in physics all the time. It's kind of almost a bit of physics, which is the dark horse of the physics world. We use it everywhere, but we don't really tend to speak about it much. And so things like how hot things, so what kind of light and radiation hot things give off relies on this. Lasers rely on this. All of our knowledge of how those work. Basically, any time you've got lots and lots of things, be they electrons, atoms, molecules, they all have to be treated in this statistical fashion. And this was one of the things that Einstein did all the way back in 1905. Thank you.